Good afternoon. The title of my talk today is on HHG and Supercontinuum Generation for intense femtosecond visible and near-infrared pulses, based on the Kerr response times of different states of matter. That means gases, liquids, and solids. HHG and supercontinuum are nonlinear optical effects that can be described by electromagnetic theory arising from the Kerr effect. My name is Robert Alfano. I am from City College. This is a picture of the supercontinuum. The focus of this talk is based on try to understand fundamentally the generation of HHG and supercontinuum based on generalized electromagnetic theory. It all started in 1875 with John Kerr, when he used a DC electric field on a liquid to induce a nonlinear index of refraction, which changed the state of polarization of the light passing through it. In 1956, Buckingham, 75 years later, showed that an AC effect and suggested some salient features. He had a power supply that turned on and off, and he used that for the Kerr effect. And he said in his paper in 1956, he said, there's no reason why the index of refraction can't be instantaneous. That's number one. That means it follows the optical cycles. The average, and then he said, we could average over many cycles to get an average Kerr effect. And more importantly, he mentions in a couple of sentences that if you only had a lamp that put out thousands of volts per centimeter, he would have an optical Kerr effect, but he did not have that. He had the most powerful lamps were 1 volt per centimeter. And only with the development of the laser that Duguay in 1969, 15 years later, essentially said that he's going to do the optical Kerr effect, where he used a picosecond laser pulse, which had 10 to the 5th volts per centimeter, and he found the light changed of a probe beam, changed the state of polarization of the beam. Now, the basis of the optical Kerr effect is based on the laser electric field. It's key to know that it travels through the medium, and the shape of the pulse is the envelope, and inside the envelope is the optical field, optical cycles, and both phenomena causes new processes of the medium. So there are two parts of the electric field. The first part is the Gaussian or the Lorentzian pulse shape, or secant pulse shape, and times the phase. And these two things cause interesting effects. The fact that the phase of the wave, this is the phase, gives rise to HHG. We're going to show that clearly, that the phase causes not only the HHG, but the self-phase modulation about each HHG pulse, but the envelope gives rise to self-phase modulation. All the theories that were based on self-phase modulation supercontinuum use the shape of the pulse. They did not use the optical cycles. That's the key here. Only in 1972, when Hope, Alfano, and Shapiro showed that it's based on the self-phase modulation can be generated from the optical cycles. The key behind the Kerr index is its size and response time. There's two parts to N2. It can be a sum of different mechanisms that arise. So N2 arises from different type of mechanism that causes the change in index of refraction. There are electronic cloud, molecular redistribution, ionization, plasma formation, rotation. Each one of these has its own response time. For example, the ultra-fast response due to the electronic cloud distortion is 50 attoseconds. The fast part, which is a tenth of a picosecond, and the slow one, 1 to 10 picosecond. So So as I was saying, the N2, the ultra fast passes 50 attosecond. The fast is 100 femtoseconds, and the slow is 1 picosecond. So this talk will be concerning about the ultra fast mechanism of N2 in the 4 states of matter, which is gases, liquids, and solids, and plasma. And the generation of HHG. So we will show that the fast mechanisms will do that. So the mechanisms for the Kerr effect N2, which is based on chi3 and the response time. Here's a cartoon picture of the different mechanisms. Here, the electron cloud is initially you have a ball of charge, like an egg, and then you put the electric field on it, and the electron cloud will change into an egg shape, and that's on the order of 50 attoseconds, 1/3 of the Bohr orbit, to 1 femtoseconds. So different materials will have different response times of electronic origin. Molecular redistribution is 100 femtoseconds to 1 picoseconds, where it changes the molecular shape. The other mechanism is the rotation and vibrational time of a molecule, which is 2 to 10 picoseconds. And the plasma formation is on the order of 100 femtoseconds. As I said before, the Kerr response time is key and can be represented by Ft of tau, where the index Nt is equal to delta n, where delta n is now using the response function of the Kerr medium times the electric field. So this is F of t is equal to N2 e to the minus t over tau. So this is tau is the response time of the material. The electric field of E of t is given by what I said before, is the Gaussian times the phase part of the electromagnetic wave. So we will stick in N of t with the instantaneous response, and one can obtain an instantaneous response to the electric field through the Kerr index. But the key here is we're going to add a response time to the material. So that's the key to the different generations. Oh, son of a gun. One could use the instantaneous index of refraction or average over a portion of the index responding to the index response time of different media, where we put in a response function, N of t. Now, every medium, every peaceful scene in nature, as we see here, has really a riot of activity due to the molecules in the various regions. So you need a clock. I need a clock to understand the molecular world, and that's the picosecond and femtosecond laser pulses. So the picosecond laser pulse is the second hand of the clock, and the speed of light is the mechanism to turn the light, to move the clock. Now, the salient properties of light is shown in this slide, where we have color, which is this is the sine wave, which shows here's part of the supercontinuum, and time. You have the pulse width, which acts as the key mechanism of clocks. We have polarization, which is linear and circular. The light can be, laser light is coherent, matching in states. And a new process is the wavefront. The wavefront can be plane, which is the typical one that everybody uses in optics courses, but it also can have a helical and spiral nature. So it comes out as a donut. So these are the forms of light we use in the process. Now, comparing the laser light and supercontinuum, light comparing shown in this slide. As I was saying, with comparison of laser light and supercontinuum is shown in this slide. Here's a typical laser beam on the wall. It's red. It's a nice Gaussian profile. Its spectral width is much less than the delta lambda is much less than the wavelength. That's a typical laser. But a supercontinuum light is white. It comes on the wall as white. You'll see that in a minute. It spans all the wavelengths from violet to near infrared. And the delta lambda is comparable to the wavelength. So that's very broad. Yeah, in 1970, the discovery was made by Alfano and Shapiro in 3 phys rev letters. In volume 24, 584, 592, and 1217, where they observed the angular pattern of the emission coming from a sample. And this is the angular pattern looking head on at the beam. And this yellow and red is the supercontinuum. And the rest of it is 4-wave mixing. And you can see that on the slide below, where you have a 5 picosecond pulse, 5 picosecond pulse traveling into peaks of glass. This is the Rayleigh scattering you see. These are some filters to eliminate the green light, and you see a pattern on the screen. You see this pattern in the red. And if you put blue filters here, you'll see blue. This was the observation. And we're stuck again. Here we show an example of the supercontinuum. What happened to the arrow? So as we said, the laser beam is coming into the liquid cell. You see the generation of the light changing to the liquid, and you see white on the screen. So that's total conversion of the light, the laser light at 800 nanometers to white. The underlying basic mechanism of supercontinuum is shown in this slide, where the phase of the wave, as I said before, is given electromagnetic waves omega t minus n omega c, and the index of refraction, as we said by Kerr, is n0 and 2e. You stick the index of refraction into the phase, as we see here. You put the index of refraction into the phase, we get the phase of a wave given omega t minus n0 and 2e squared. And the derivative of the phase is the frequency, a new frequency, which gives the supercontinuum broadening. As we see on the right side, here's the envelope of the pulse, and the derivative of this gives you the sigmoidal shape, which gives rise to the time dependence of the pulse generating the continuum. So you get the continuum is the span of the frequency depends on n2 I z over tau, the pulse width of the laser. So this generated the picosecond effect and a white light continuum. The Fourier transform is used to get the S of omega from the time. Stop it. The key is the response time of the nonlinear index. Okay, that's the key. And I'm repeating myself, but the response time mechanism of the nonlinear index of refraction, N2, depends on the underlying mechanism, which I showed before, the electronic molecular redistribution, rocking, orientation, translation. Each one of these has a different response time. The electronic is 10 attoseconds, 100 attoseconds here. Molecular redistribution, sub picosecond, 100 femtosecond, rocking, picosecond, orientation, a picosecond, and translation. So this essentially is the key of generating HHG when your response times are less than 10 to the minus 13 seconds of the medium. So the ultra-fast index, as I said, depends on the phase in the envelope, and that gives rise, we'll see, HHG and supercontinuum. The slower mechanism is an average effect and gives you rise to cell-phase modulation or supercontinuum. It's jammed. Again, repeating myself, the ultra-fast, the index of refraction and instantaneous index, but it depends on the phase in the envelope, gives rise to HHG and supercontinuum, and the slower one gives rise to cell phase modulation. So the research we're going to be talking about now is how we get HHG. I'm going to show that it depends on the material NFT and the envelope and phase. On the envelope and phase, well, self-phase modulation, supercontinuum depends on the envelope. That's going to be shown in a few seconds. Locked. So the HHG depends on the envelope and phase, while the supercontinuum depends on just the envelope. And this is a cartoon of the type of spectra you get when you have the mechanisms of self-phase modulation and supercontinuum. When you put in a laser at omega 0, the supercontinuum due to self-phase modulation spans symmetrically about the laser, and it goes from, let's say, up to 2 omega almost down to 0, while the odd harmonics start at 3 omega, and there's three characteristic features that there's a slow ramp of generation of odd harmonics, a flat plateau, and a cutoff frequency. So those are the salient features that you get in supercontinuum and self-phase modulation, depending on self-phase modulation, which gives rise to the spectral broadening around the laser. Now, notice if the laser goes to 2 omega and it's symmetrical, that the continuum would span from 0 to 2 omega, and then omega 0 subtract off, and it goes to 0. So the supercontinuum should be able to go from DC up to 2 omega at least, and it goes beyond that. So, and then if it goes beyond 2 omega from the laser, then you go into the negative frequency regime, which is an interesting phenomena that you can generate negative frequencies from self-phase modulation, and that's why it's called ultra supercontinuum. Now, I'm going to be talking about the odd harmonic generation and following the instantaneous and Nixon refraction. So in this case, we're going to talk about the material response to the electronic origin, and we're going to see that when you do that, you get odd harmonic characteristics. And the fast underlying mechanism is going to do with electronic being in various materials. If you have rare gases, the only mechanism you have a ball of charge, which is the argon, krypton, neon, and xenon. You put the electric field, the ball of charge becomes an egg, and that's essentially gives rise to N2, and that gives rise to the instantaneous Nixon refraction. Now, depending on the material, and a solid would be the electronic response, which could be up to a sub picosecond or a femtosecond response times. And the underlying mechanism for the electronic self-phase modulation is that you take the Nixon refraction, which has got the N2E squared, this is the electric field squared, and this is the phase. And if you stick that into the phase, you get the NFT of the electric field, and then you take a power spectrum using a Fourier transform. And this is the key slide that we have here, that the results of electronic self-phase modulation, where here is the electric field of the laser, here's your Gaussian, here's your phase, here's NFT. We stick in NFT into the Gaussian and its phase, and then you take a Fourier transform and you go to omega space, and you get the omega intensity, the intensity of the light and frequency domain. And this shows the characteristic spectra of the intensity of the S of omega at different omega. You see that there are 3 regimes: decaying odd harmonics, a plateau, and a decreasing cutoff frequency. And around each of the odd harmonics, you get supercontinuum around each odd harmonics. And so that gives you a spectral broadening. So the 3 key features of HHG from this electromagnetic model, this is the electromagnetic model that you have, that there are 3 regimes: the steady decline, that's in region 1, followed by a plateau, region 2, and a cutoff. These are the characteristics that you see experimentally, that people have seen this in the late 90s and the 200. And nowadays, they used to do only, in the past, they only used argon and rare gas molecules. Now, Reese from Stanford and others have used solids and generated autoharmonic generation from solids. And so far, autoharmonic generation is not only done in rare gases, but liquids and solids. And you could explain all these by this electromagnetic model. And this is higher intensities. Here we put in at 6 millijoule pulse in argon gas. You generate the characteristic features. This is the experiment. This is the theory, seeing that the cutoff is similar to the experiment. And if you raise the power, double the power, the broadening gets longer, its cutoff frequency goes out to further double the frequency broadening, and you still get the characteristic 3 fingerprints from this theory of electromagnetic model that you get 1, 2, and 3. So the ansatz of the whole thing that we put forward is the response time of N2. When you use the response time, you will find that it limits the HHG totally. That if there's a response time to the index of refraction N0, they put this response time function F, which has got tau, the relaxation time of the material, you will then affect the number of odd harmonics. The cutoff frequency changes with the response time. So this is a key slide, that theory slide. HHG response times for argon medium with 50 femtosecond pulses shows the cutoff frequency of HHG for different response times. Underneath the slide here is the response times. This is for a tenth of a femtosecond. That's like 100 attoseconds. Here's one at 1 femtosecond, and here's 10 femtoseconds. You're still using 50 femtosecond pulses, but the response to that 50 depends on how much cutoff frequency you get. So a tenth of attoseconds, you get all the way out to about 51 frequencies in the UV for HHG spectra. But if you go to 1 femtosecond response time, it goes down to 10 omega 0. So that's 10. This one's 51 omega 0. If you use 10 femtoseconds, it only goes down to 1 of the hot harmonics. So it's critical that the response time of the medium has to be fast, and that is electronic origin, depending on the material you use. So if you have a material like argon, that's and krypton and rare gases, that's all something of the 100 attosecond response time. Or if you do a solid, such as zinc oxide or some glasses, then you would get harmonic generation up to about 10, and it really depends on the response time of the electrons in the solid. And the thing on the bottom here, the bottom part of this slide, shows the spectral broadening around each harmonic, around the harmonics that you see in the upper slide here. Is the spectral broadening, which is not seen using the theory of quantum mechanics. The mechanism I should talk about briefly is the mechanism that people have used in the past, is this tunneling followed by acceleration, part of return to the atom. This is a very crude mechanism to get HHG. The electromagnetic theory seems to be a much simpler and get all the characteristics of the parameters used in these different materials, such as solids. The quantum mechanical model cannot be used to generate these frequencies in solids. I'm stuck. So it's critical of the response time of the material being under a femtosecond to get significant HHG. So that's the key. Otherwise, you just get spectral broadening. The slide on the bottom is the spectral broadening associated with each of these response times of the Kerr medium. Remember, the pulse width is 50 femtoseconds or a picosecond. It doesn't matter. What matters is the response time of the material. Here, this slide shows the number of odd harmonics, which is the y-axis, and the x-axis is the response time of the Kerr medium. Now we're talking about argon, zinc oxide, lead glass for response time for picosecond and femtosecond pulses. So that's the pulse width, but the response time is key, but is on the x-axis. So you see the number of odd harmonics up to 31 or 29 here goes down significantly to about 5 for something on the order of 10 femtoseconds. So 10 femtoseconds in argon for a 90 femtosecond pulse or 1 picosecond pulse depends critically on the response time that you get from the theory. So and the response time of the medium is critical for generating odd harmonics. There's zinc oxide, which is a solid at 1600, done by Reese's group, and he used 50 femtosecond pulse, and he obviously zinc oxide. The electronic response is on this order of magnitude. You would get this number of odd harmonics. The cutoff frequencies depend on the response time of the medium. Otherwise, it goes down to 5 when it has a very slow response times. This is some experiments done by Reese's group in solid argon and krypton. He sees the characteristic odd harmonics for 26 terahertz per square centimeter or 16 terahertz. So this is in argon, and he also did it in solids. The Reese group from Stanford, which also asked for he suggested that there's a theory needed for odd harmonic generation in solids and liquids, and so this theory of electromagnetic model is critical for the Kerr effect that gives rise to the odd harmonic generation in materials. So in conclusion, I guess one could explain HHG explains from the Kerr effect responding to the optical cycles of the laser. So it has to respond to the optical cycles of the laser. What happened here? So the key is the Kerr index following the optical size in rare gases and solids. Explains the 3 regimes that can be found in the electronic cell phase modulation model based on the response time of the Kerr medium. That's the key to develop the simpler model for generating HHG. And you can find a lot of this work in the paper on the bottom here. Which is high harmonic generation. Alfano, Mazer, Shi, in Optic 24, 2021, gives the main paper on the instantaneous Kerr effect, which you essentially have a 50 attosecond, 100 attosecond response time for the Kerr medium, and it is really a new paper is being published on the response time of the mechanism going on what I presented in this talk, that the response time of the Kerr medium beyond 50 attoseconds shortens the number of odd harmonics you get in the observation of the theory. Okay, so you get that paper, and we're stuck again. I hope I gave you a clear explanation of the outcome of this paper and showed that a universal electronic cloud model or theoretical electromagnetic model for the interaction of femtosecond and picosecond pulse depends on the Kerr response time, and it could be Kerr in gases, liquids, and solids, depending on the response time of the material and where you generate HHG and supercontinuum. HG is caused by the phase and envelope of the pulse, and really is instantaneous to less than a femtosecond response time of the medium, and not the pulse width itself. So the medium has got this N2 and its response time. Wow, if you're just talking about, you cannot generate HHG from a pure slower picosecond process from the envelope of the mechanism. So the envelope gives you just supercontinuum of self-phase modulation, while the response time of the Kerr medium from the optical cycles, responding to the optical cycles, is key to generating HHG. And this is a more universal model and depends on the response time of the material you use, be it a gas, liquid, or solid, or plasma. So these all generate HHG if you have a response time that's on the order of a femtosecond or less. Thank you very much. I'm sorry that this is so choppy because we had a problem with my computer. So thank you very much. Thank you very much to all my students, researchers, funding agency, and Ms. Sentry for assistance with this presentation. I'm sorry it's so choppy, and sorry I didn't make it to California because of the hurricane going to San Diego. And I thank Professor Shi for helping out on this. And part of the original work done at City College was done with Mazur and Shi. And thank you very much.